Welcome to the deep dive. Today we're going to drill down into a really fundamental question about AGI. Why haven't our most advanced AI agents, the ones
Yeah,
built on these huge LLMs and reinforcement learning, why haven't they hit superintelligence in software yet?
it's a great question. And the research points to something that isn't about raw power, but a lack of independence. Basically, the agents we have now are stuck. They're in this cycle of human dependence.
Human dependence, what do you mean by that?
I mean, they rely completely on curated data sets. Think GitHub issues, pull requests, tests written by people. And if you only train a model on human fixes for human problems, well, you've just built a feeling, haven't you?
Ah, okay. So they'll only ever learn to be as good as the average human solution. They can't find some truly novel, non-human way to optimize things.
Exactly. They can't think outside the box we've built for them.
So the bottleneck is us, the programmers. And to get past us, the agent has to escape our data.
Right. And that's where this research comes in. They're trying to build that escape road. It's a method called self-play, SWE-RL, or SSR for short. And it's really positioned as a first step toward a totally autonomous way of training.
Okay, so let's get into SSR. What's the breakthrough here?
The breakthrough is its minimal data assumption. It's actually pretty radical. It just needs access to sandboxed repositories, the source code and its dependencies. That's it.
So no need for a person to write up a bug report.
None. No natural language issue tickets, no pre-written tests from a dev team. We're taking the human curation out of the loop.
Wow. Okay, so how does it learn then, if we're not feeding it problems?
This is where it gets really interesting. The agent trains itself. It's a pure self-play loop.
Self-play, like in games, like AlphaGo.
Precisely. It becomes both the adversary and the hero. The agent starts by iteratively injecting software bugs into the code.
And then it tries to fix them itself.
And then it tries to fix the very bugs it just created, and it keeps ramping up the complexity over and over.
So this raises a critical point, I think. The agent isn't reading a ticket that says, the login button is broken.
No, and that's the crucial distinction for you, the learner. The bugs are formally specified by a test patch.
Wait, a test patch? Let me just make sure I'm getting the significance of that. If it's only operating on a test patch, that means it's all just pure logic. There's no human context or language involved.
That's the key. Think of it like this. Instead of a human saying, my car is making a weird noise, the system is just given a technical spec. It's a spec that shows the engine's RPM objectively dropped by 500 at a certain point. The task is just to restore that objective state.
I see. So it doesn't matter how a human would describe the problem. The learning loop is totally self-contained and objective.
And scalable. Massively scalable.
But I have to ask the skeptical question. If it's making its own problems, how do we know they aren't just trivial? Couldn't it just be training on simple stuff that doesn't really translate to the real world?
A fair question. But that's where the performance data comes in. The proof is in the benchmarks. When they tested it on standard software engineering benchmarks, SWE-bench verified and pro, the agent showed these remarkable gains. We're talking plus 10.4 and plus 7.8 points.
And just for context, these benchmarks aren't simple. They represent fixing really complex, real-world bugs in big libraries like Python and JavaScript, right?
They are. So these are not trivial wins. This autonomously trained agent is now significantly better at fixing hard problems than the models trained specifically on human-curated data.
That's incredible.
But here's the part that's genuinely surprising. The agent got these results even though it was evaluated on tasks that were described with natural language issue descriptions.
Wait, what? But it never saw natural language in its training?
Never, which shows this incredible generalization. It learned the core logical principles of programming and then was able to apply them to messy human communication structures.
So this really does connect back to that grand goal of superintelligence. It suggests there's a real path where these agents can just autonomously gather almost limitless learning experiences, bypassing us entirely.
Precisely. The promise here is that this kind of method could lead to systems that exceed our capabilities, not just in speed, but in really understanding how complex systems are built. And then from there, solving challenges we've never even seen and creating brand new software from scratch.
So the core insight we've pulled from this is pretty clear. The key to superintelligence isn't just more human data, it's the self-generation of learning experiences.
It is. And here's the final thought I want to leave you with. If a machine can learn to create and fix incredibly complex bugs using only these formal logical test patches, how long until its understanding of how to build systems becomes so abstract, so sophisticated that it's just, well, completely opaque and unrelatable to a human programmer?